unmute myself. Let's hope this works. Okay, I'm really bad with technology. So section 9.1, which is linear and nonlinear systems of equations. So what is a linear equation? It is a set of two or more equations whose variables are all to the first power and that we can use to solve for said variables. So the one on the left and the one in the middle are both examples of linear systems of equations, even though the one on the left has 3 variables and the one in the middle only has 2. Now this one on the right here is not a linear system of equations, it's actually a nonlinear, because you can see that the first equation has an x to the second power. So we call it nonlinear. Now we're going to start with a super easy equation, which is x plus y equals 3 and y equals 3. Now we're going to take the first equation, we're going to rewrite it as x plus 3 equals 3, because we're going to plug in the y from the second equation into the first. And then we see that x equals 0. Now we're going to check it. We're going to write 0 plus 3 equals 3 and y equals 3. And since they both are true, it's going to be x equals 0 and y equals 3. Now we're going to do a little bit hard of an example, which is going to be x plus y equals 9, and 2x plus 3y equals 5. And again, we're going to rewrite the first equation so we get one variable on the left side. So we write it as x equals 9 minus y. Now we're going to plug the 9 minus y into the second equation, and it's going to be 2 times 9 minus y plus 3y equals 5. And then we're going to distribute and simplify, so we get 18 minus y equals 5, and we get y equals negative 13. Now we're going to take the negative 13, we should have done that, and we're going to place it into the first equation again. So we get x plus negative 13 equals 9, and then we see that x will equal 22. Now we're going to plug the 22 and the negative 13 into the first and the second equation, and we see that they both are true, they both work. So we know that x equals 22 and y equals negative 13. Now we're going to try a word problem, and that is going to be Louise sells hair bows and flower crowns. It takes her 3 times the amount of roses and 5 times the amount of daisies to make a flower crown instead of a bow. If she uses 21 flowers for a crown and 5 for a bow, how many of each flower does she need to make a crown and a bow? So then we're going to say x equals roses and y equals daisies. And then we're going to write x plus y equals 5 for the hair bows and 3x plus 5y for the hair crowns. And then we're going to rewrite the first equation again so that x equals 5 minus y. Then we're going to plug in the x equals 5 minus y into the second equation. Then you get 3 times 5 minus y plus 5y equals 21. You're going to distribute and simplify so that 15 plus 2y equals 21, and we see that y equals 3. Okay, now you're going to put in the 3 over here, and you get x will equal 2. Now we're going to check both of them in the first equation and the second equation, and you see that they both work. So then the question says that you want to make 1 crown and 1 bow. So you're going to do 2 for the crown plus 2 for the bow plus 6 for the crown, and that equals 8. And then 3 for the bow and 15 for the crown for the daisies, and then that equals 18. So Louise needs 8 roses and 18 daisies. Now we're going to look at a graph. We're going to take the system of equations from the second problem, and again it's x plus y equals 9 and 2x plus 3y equals 5. And I already graphed it here, so you see that's what it would look like. And you can see that the lines intersect at 22 and -13, which if you remember from the second problem, those are the x and the y that you get. So by graphing these, it's a lot easier, it's a lot quicker, and you can actually visually see how the point intersects and how the lines work together. And we can actually use this as a pretty easy way for nonlinear systems. So for this problem, we're going to use the system 5x plus 6y equals 21 and x squared plus y equals 9. And here we have the graph. And we're just going to quickly plot them. The blue is going to be for the second equation. The pink is for the first. And you see that the points of intersection are -1.96, 5.14, and 2.8, 1.16. And now we're going to plug in both of these into the first and second equations. We're going to do the one on the left first, and you can see that they're pretty close. They basically work. So we know that this is a solution point, and then you're going to do that for the second one, and you can see that 2.8 and 1.16 are also both valid equations. They're both valid points for this graph. So x and y can equal -1.96, 5.14, or can equal 2.8 and 1.16. And you can also solve nonlinear systems of equations by, once again, isolating the variable, and then you're going to need to complete the square for these in most cases, because it's the easiest way to solve them. But again, graphing is probably the easiest way, the most visual way to solve a problem. And for engineers, it's kind of the cop-out cheap way. So now, before we wrap this up, we're going to talk about different solution points for linear systems of equations and nonlinear systems of equations that only have two variables. Because once you have 3 or more variables, you get a bunch of different planes and it gets intense. So the first option is no solution, where you see that neither point, they don't intersect at all. The second is one solution. So like this, you can see that they only intersect once. You can have two solutions. Like here, you see that they intersect here and here. Or you can have an infinite amount of solutions where they all are the same. So yeah, that is it for this unit. I hope that you found this helpful and that you can use it at some point in your future. We're going to stop the recording somehow.